All right, so this is section 3.5, implicit differentiation. Okay, so basically you're taking derivative in general, and then solving for a specific derivative. So let me show you the idea here. So let's say you had, I don't know, let's make up an example real quick. Let's say I had x plus y equal to 5, right? And I took the derivative of everything with respect to x. Okay, so that would be d dx of both sides. So if they match, then you follow the same rules, right? Derivative of x is no big deal. We've done that many times. Derivative of y, let's make it a little more complicated. Let's make it a y squared. Otherwise, it's not as interesting. Y squared equal to d dx, right? So we know the derivative of any constant is 0, so that's easy. Derivative of x is just going to be 1. So the different one is this, because these don't match. So this is derivative of y, but with respect to x. So this is where it gets weird. So you have to do a power rule like we usually do, bring down the y, but then multiply by an implicit chain rule. So you multiply by dy dx. So this piece is the new thing for this section. Okay, now if we use the other notation, let's say we did. It makes more sense to use this notation, but some of you may not like it. So I'm going to try to use the y prime stuff. So if I took the derivative of both sides with respect to x, so this is where it doesn't really help. It's because I can't really say it's x, right? But let's pretend that we knew it was going to be x, right? Using the quote. So this would be derivative would be 1. This would be 2y times y prime equal to 0. See how it's almost the same? The only issue is you have to make a mental note that I'm taking a derivative with respect to x, and that must be known. But if there's like more than one variable, then it can get confusing. Okay, but the question will tell you. But that's why we're going to start using ddx on these examples, so it's clear with respect to what variable we're doing. So let's look at the first question here. So example 1, you see how there's x's and y's. They want you to find dy dx. So this is giving you the hint that take the derivative of each one with respect to x and then solve for dy dx. So you got to isolate this piece implicitly. That's the idea. You can outright solve for it. So we're not doing a direct derivative. We're doing an implicit derivative. So this is example 1, problem 1 from your homework. So that's going to be, let's see here, 3x squared minus 7y squared equal to 1. Right, that's what the question said, and it wants us to find dy dx. So what you have to do is do d dx of each term, and then of both sides, of course, and then do that little rule I showed you, the dy dx. So these match up, so you would simply just say 6x. You bring the 2 down, subtract 1. This is the same it's always been because they're the same variable. Over here, though, they are not the same. So it starts off similar, but then you have to multiply by the derivative of y with respect to x. So really, that's the only new thing we're doing. Does that make sense? We're just adding this piece here. Is there any questions up to this point here?
Does the d over dx not match with the y, the 7y squared, because it's a y instead of a x?
Yeah, exactly. Yeah, because it's not the respect to the same variable. Since it's respect to a different variable, you have to add this piece.
Okay.
So just think of it that way, and you should be fine with the implicit stuff. So you'll, if they don't match, like let's say I did a derivative instead of dx, I did dt respect to time, and they're both x. Then this is an x and that's a y, and there is no time anywhere. Then you would have to do both of them like this.
I was wondering if you could back up a little bit. I my computer kind of messed up and I missed kind of the beginning part.
Yeah, sure, man.
So sorry about that.
Yeah, the beginning I just made up an example to try to show you what's going to happen today. You're talking about this problem, right?
Yes, sir.
So basically, I said, like, let's say we had a function with, or an equation with an x and a y. And if I did derivative with respect to x of both sides, then you would have to do d dx of each part. This makes it more clear that we're doing with respect to x. So
Okay.
if they match, you just do the same old that we've been doing, derivative rules we've learned up to this point. Derivative of x is 1. Derivative of this, you have to do a power rule like usual, but because it's not matching, you have to tack on the dy dx here.
I see.
Derivative of a constant is 0. And then the next step would be to solve for this, which we're going to do on the next example.
Oh, okay. All right. Sweet.
So that's pretty much what we did here. So d dx on every single term. This is 0. This is the new thing. So power rule, tack on the dy dx. Derivative of 3x squared is the same because they match. You just follow the basic power rules, giving us 6x. Now we solve for this guy.
Okay. That makes sense.
So move this guy to the right-hand side, make it positive. So now I need to divide both sides by 14y. So these cancel, so that means that dy dx is equal to 6x over 14y, which is what? It reduces to 3x over 7y. And this is what they have here. This is what they want you to do. They want you to find, take the derivative of each term with respect to x and then isolate the dy dx from your equation.
What kind of application does the implicit form of the derivatives have?
That's going to be the next section. It's very applicable. Basically, if you had a real life problem where x and y might be, let's say, some sort of growth variables, or maybe I think the famous popular example would be, let's say you have you're pumping air into a balloon, or like a hot air balloon or some sort of object, or you're filling it with water. So the x and y could be the dimensions of the object that are expanding over time. So when you take the implicit derivative with respect to time, you can solve for the rate of growth or expansion on the x or expansion on the y. Or I think the other famous example is when there's like a ladder falling off or sliding off sliding down a building or something. So they'll tell you, okay, as the ladder is sliding, what is the change in the X, the base of the ladder, whatever the shadow made versus the height or something. So it becomes pretty applicable all over the place, which we'll do pretty soon.
Oh, okay. Okay, sweet.
Just remember that dy dx, right? What are derivatives? Well, they mean all kinds of things, but for sure, or the most important thing is they are rates of change, right? So right now it is just a general problem. It doesn't really mean anything. But once we assign things to x and y is a rate of change over some time or some distance. Depends. Okay, let's see here. Let's do another one. This one looks kind of funky. Number 3. Notice how here we have a product. So we're probably gonna have to do a product rule, but during the product rule, we're gonna have implicit pieces. And notice how we can't solve for just one variable. That's why it's called implicit. It's gonna be a solution with x's and y's. We cannot isolate them. So let's do number 3. An example, let's say 2. Problem 3. Okay, so find dy dx by implicit differentiation. All right. So the question they gave us was x to the 4th, y to the 8th, minus y equal to x. So they want to find dy dx. So this is the hint that I should take the derivative with respect to x on every single term. So d dx of the first term minus d dx of the y term, d dx of x term. Okay, so this one's no big deal. It's just going to be a 1. This one is going to be the frustrating part because we have a product. So we're going to do derivative of the first, right? Times the second plus derivative of the second times the first part. So there's my product rule minus the derivative of y, which is just going to be 1 times dy dx equal to 1. Okay. Any of these steps, you guys still with me on the spot? Do you see what happened?
I'm kind of lost on that part right there.
So you see that we need a product rule, right?
Yes.
So you got to take the derivative of the first times the second plus derivative of the second times the first, right? That's just the formula. So the derivative of the first part times the second. So I'm using this notation instead. Plus derivative of the second part times the first.
Oh, so you're just using the product format for that first one?
Yeah, this right here is just product rule. The derivative of y is 1 times dy dx. So that's the new implicit rule. derivative of x is 1. If they're, respecting the same variable, of course. So now we have to do the implicit derivatives, right? Derivative of x to the fourth, well, these match up, so who cares? That's just a basic power rule, right? This one is going to be implicit, so it's going to be 8y7 times dy dx times that x to the fourth is just there, just hanging out. Okay. You guys okay so far? To this point, the implicit derivative is done. Now we just have to solve for dy dx. That's it.
How come you didn't take the derivative for the x to the fourth power?
I did right here.
No, I mean on the very right side.
This one?
One more. Yes. that
Well,
one.
this is the derivative only of this piece.
Oh, okay. Okay.
Right, this is the chain rule right here. Derivative of the first term times second plus derivative of the second term times the first. So I'm only doing derivative of the part that is attached to it.
Okay, that makes sense.
So derivative of this guy is right here. Derivative of x4 is here. So these remain unchanged right there. So at this point, just isolate anything that has a dy dx on one side. So I'm going to move this guy to the right hand side. So that'll give me 8y7 dy dx minus dy dx equal to 1 minus 4x cubed y eighth. Factor dy dx. So that'll be 8y7 minus 1 equal to 1 minus 4x cubed y to the eighth. So I factored the dy dx out of both terms, right? Over here, all I did was move this guy to the right-hand side via subtraction. So now divide this out and you're done. So sometimes the algebra can get messy during the implicit. These are gone. So that is my solution. Dy dx is equal to 1 minus 4x cubed y to the eighth over 8y7 minus 1. Shoot, did I forget something? One moment, I feel like I did. Yeah. My x4, I forgot to write that. So no biscuit. There should be, see how I just stopped writing it for no reason. Sorry about that. So this should be right here, x4 minus dy dx. So that means right here, There should be an x4 minus 1. So, man, I hate when I make a mistake right at the beginning. And we'll go over it again just to be safe, in case I confused you. So there should be an x4 here. 8y7 x4. 8y7 x4. 8y7 x4. There we go. Now it's fixed. So we finished the derivative here. So the algebra that I had messed up was, I need to subtract this on both sides. And that gets me to here. And then I need to factor dy dx from both of these terms. So when I factor it out here, I'm left with this term, 8y7 x4 minus 1, because I'm factoring the entire thing out. That's the same. So then we divide this piece out here. This cancels, leaving me with dy dx. So our solution will be this guy. And that's how they got their answer here. Are there any steps that didn't make sense? Either the implicit part or the algebra part? Okay, let's do another one. This entire section looks like it's just the same thing over and over again, just different forms. Let's see. Delete some of these problems here. All right, let's do 5, I guess. So find dy dx by implicit differentiation. Okay, so x times e to the y minus 11x plus 7y equal to 0. So this here will be a product rule again. We just have to deal with that e to the y. So we'll do the derivative of every term. Most of these will be easy, except that first one. Technically, you do the derivative of 0, but that's still gonna be 0. Who cares, right? This is a product rule, so let's set up using the formula. So the derivative of the first times the second plus the derivative of the second times the first part plus derivative of 7y is going to be 7 dy dx equal to 0. So I did this derivative here, and I set up the product rule for this first two parts. Oh man, I forgot the 11. Let me rewrite that. I forgot something. Derivative of the 11x is going to be negative 11 times, actually they match, so it's just negative 11 plus 7 dy dx equal to 0. There we go. Any questions on these derivatives and the product rule setup? Okay, so far so good. Derivative of the x will be just the 1 times e to the y plus derivative of this guy will be, it's going to be itself, but with a chain rule attached. Sorry, I have some family over today. So e to the y times dy dx. Okay. E to the derivative of this guy is itself times the chain rule times that x right there. Derivative of that, I'll double check everything. Yeah, now we're good. Okay. Any questions on the product rule? Does that make sense? Okay. So then we're back to the algebra step. Solve for dy dx. So get this on one side and factor it out. Move everything else to the right hand side. So this will be, go ahead and group it together right now, dy dx. So these are the dy dx parts here. Then we're going to move over these pieces to the right. So minus, right? So minus e to the y. So I'm subtracting this guy on both sides. Plus the 11. So as these two are here, these two have been moved to the right. So when you move them, you just swap the sign. That's how I like to think about it. Instead of subtracting both sides, you're adding both sides. Move ey to the right, now it's negative. Move 11 to the right, now it's positive. Same thing. You can think of it however you want, but we've isolated dy dx and stuff that doesn't have dy dx. Now we can solve for it by factoring. This side is just going to be divided into. So divide both sides by the 1 and x. And I did this x, right?
No, I think that was left out on the second to last one.
Here. Yeah, this one's good because it's just the one. The one doesn't do anything, so that's fine. But this X here should be right there. So let's make that look a little prettier. I don't know why I keep forgetting that little piece. It's the second time I do that. I guess I'm still a little out of it. So the X will be right there. Ey to the X, Ey times X plus 7 is what I'm going to divide out on both sides. There we go. So divide it out. Dy dx will equal negative e to the y plus 11 over e to the y x plus 7. Okay. So now any questions on any of these steps? So this section is going to have all the rules and ideas from the chain rule, product rule, quotient. So while you're doing an implicit derivative, it could be a quotient, could be a power rule, could be whatever. Could be a really easy one, could be a really hard one, but the idea will be the same. You need to tack on the dy dx whenever it doesn't match. Okay. Okay, one moment. Okay, so find the same question is the same thing. Example 4. Find dy dx by implicit differentiation. Okay, so y is equal to sine of xy. So notice how when we do the derivative of sine, we're going to have to do, we have to multiply by the derivative of the inside. So this is a chain rule, which will trigger a product rule. But while you're doing all that, it's going to be implicit, right? You have to follow the implicit rules. So the derivative of both sides the derivative of this guy is just dy dx equal to derivative of sine is cosine xy, right? Times the derivative of the inside. This is the chain rule. I'm just using the other notation. It's the only difference. So dy dx equal to cosine xy. Derivative of xy is going to be, I'm going to put brackets here because that's we're going to be working on these two. So derivative of x, so this is the product rule. It's a derivative of this guy times my y plus derivative of the y, right, times the x. Okay. Okay, so that part makes sense.
What rule did you use? I'm sorry, my computer kind of like kicked me out. Well, is this chain rule? What is this?
Okay, so when this entire section is implicit differentiation, right? We're doing implicit
but
derivatives. So
Yeah.
when we do
Oh.
d dx of both sides, but while we're doing the sign, it's going to be a chain rule that triggers a product rule.
Oh, okay. I see.
Okay, so now here we just do the product rule. So first we did the chain, then the product. So it looked simple at first, but now it just looks kind of funky. So derivative of x is going to be 1 times the y plus derivative of y is dy dx times the x. So distribute the cosine, that'll be y cosine xy minus x dy dx cosine xy. So now I'm going to move this guy over here with this dy dx and start the factoring part. So at this point, the derivatives are done.
Is that like an 11 next to the y? What is that?
The last line,
No, the second to last one on top. It's like parentheses. What is that?
so 1.
Oh, it's just a one. Oh, okay, okay.
Yeah, derivative of the x is 1. Okay. All right, so at this point, get all the dy dx's together. So I'm going to add the x dy dx cosine xy over here. Okay. So then factor the dy dx, and we're pretty much done at this point. So 1 plus x cosine x times y equal to y cosine of x times y. Divide both sides by that 1 plus x cosine. Then we are done. So dy dx is equal to y cosine x times y over 1 plus x cosine x times y. These will cancel.
So just to make sure that I'm understanding this correctly, if there's an x term next to the d over dx, that's when you would do the derivative for that. But if it's a y term, you would just put dy over dx and you won't do the derivative.
No, you do the derivative no matter what.
Oh, okay.
So the derivative of y is 1 times dy dx.
Okay, that makes sense.
Like the first example, we had a y squared, right? And then we pulled the two down, so we got 2y times dy dx. But if it's just a y here, right, the derivative is 1 times dy dx. If this is a y squared, you'd have a 2y here times this.
Okay.
It just
And
didn't
then-
really happen because it was a 1. That's the only reason.
Okay, so then, what is it on the third to last line?
Here,
Yes, where did you get that y behind the cosine?
let's see here. That was this one. So what I did was I distributed the cosine xy over here. This one times the y gave me this. Cosine xy times this gave me that.
Oh, okay. All right, that makes sense.
Hmm. Yeah, because we had already done the derivatives here, so this is dy dx times x. So this is that. Yeah, we're good. Okay. Any other questions on number 4? Is it making sense?
Could I ask you those questions about 3.4?
Yeah, if you guys have no questions on 3.5, then sure.
If we don't have any other questions, are we good to go, or should we?
Yeah, it's fine with me. If you need to head out, that's okay. As far as lecture goes, we'll stop there.
Okay. All right. You have a good night, sir. Feel better.
Thanks, man. See you later.
Thank you, Professor. Have a good night.
I pushed about 23
All right, have
on
a good evening.
homework 3.4.
3, 4. Let's see here. Three point 4 chain rule, right?
Yeah. I'm kind of confused on how to use the formula because I wasn't there in class, but like I was just looking at it and it just kept confusing me a lot.
What number you said? I'm sorry.
Number 23.
23. Okay. So do you understand the general idea of the chain rule?
Not really, because like when I was looking at the formula, like the way it's set up, which was just kind of confused me on like where to put the variables. So like the formula itself, I don't really understand.
Okay, let's do an easy one before we do that 23, because that one's a little harder.
Okay.
So if you don't understand the basic one, we probably shouldn't do the hard one right away.
Okay.
Let's do, so the formula that I gave you guys was this one. So there was a function within a function, the derivative would have to be done with the chain rule.
Okay.
So all you have to do is do the derivative of the outside and then multiply by the derivative of the inside without changing the inside.
So you multiply the f1 prime by the g1 prime and leave the regular g alone.
Yeah, exactly. So if our function is equal to, let's say, square root of x squared plus x, right? The inside is x squared plus x. The outside is your square root problem. I'm going to rewrite this as a power, so it's a little easier to see.
Right.
So the derivative would be a power rule. So you do the outside first, you bring down the 1/2. You don't mess with this inside, and then you multiply by the derivative of the inside. The derivative of this will be 2x plus 1, right?
Mhm.
So at that point, we're done with the derivative. So we did the outside, we did the derivative. So that's f prime right here, right?
Right,
There's g inside, I didn't mess with it. And there's this g prime.
right.
Does that make more sense or?
Yeah,
And then of course you do algebra, but who cares? But this is the main idea.
right.
So 23, so problem 23, 3.5. You want to do
3.5.
yours or 04?
Yeah, it's y equals ln e and then to the 8x.
8x, okay. So this has multiple pieces technically,
Right,
although ln and e technically cancel, so it ends up being a very boring problem.
right.
Do you see how the property, right, of logs we said back in the day, log a of a to the x is equal to x. So if these match, it cancels. ln and e match up. So the answer, the function would simply just turn into this. The ln and e's cancel. So the derivative of this would just be 8. So we don't actually have to do the chain rule here because it canceled out.
Oh, okay. See.
Yeah, I'll post it in a little bit, Ethan.
And would that kind of, well, maybe it's not the same thing, but I know whenever I finally like was trying to understand second derivatives, because the way like they would have us do it kind of confused me. I had the same issue on number 26. It's just, I was just like, I have no idea.
26. So they wanted you to do 2 derivatives. So it just
Right.
be okay. Okay, what was your problem? Mine's different.
This is f of x equals sin parentheses 2x to the second.
Is the square only on the x or is it on the whole thing?
Oh, no, it's just like, just exactly how you wrote it.
Okay. All right, so the derivative outside is sine. So f prime. So derivative of sine is cosine, right?
Right,
Times the derivative of the inside. So that will be equal to cosine 2x squared times 4x. So now we have this function as the first derivative. So we had to do a product rule. And during that product rule, you will have to do another chain. So second derivative would be, so derivative of the first part, so I'm gonna have to do it this way, times the second, plus the first part times the derivative of the second part. So this is just 4, right? Derivative of this guy is going to be another chain. So derivative outside is a negative sine 2x squared times the derivative of the inside again. Okay, so 4 times a negative, I'm just gonna make that a negative, okay? Derivative of this thing is gonna be 4x. So now we're done with all the derivatives. Now we just multiply stuff out. Four x and 4x, that'll be a negative 16x squared sine. So that'll be our answer. Any steps that that were confusing or?
Yeah, the one step that I have a question on is whenever like we're at the first line of the second derivative, when you get to the second, how come we brought 2x to the second on the outside again? Like there was like 4x and then negative sin, and the 2x to the square, and then you brought it on the outside again.
What step here?
Yeah, right, that one right there. How come we brought it out a second time, the 2x to the second?
So you understand that we're doing a product rule right here, right?
Right, yeah.
So when we're doing the derivative of this chunk right there, we have to do derivative of the outside times derivative of the inside, which is this. So we do another chain here.
Oh, okay. Because they're separate pieces.
Yeah, so all of this came from this derivative. So then I gotta
Right.
do that part here. So at this point, all the derivatives have been taken care of. So doing a second derivative is just more difficult because you already have a product from the first one.
Oh, okay, yeah, yeah, because at first I was just kind of confused. I'm just trying to like get used to like you know how at the beginning of this homework assignment, it has you practice putting like the numbers in the right places for the formula. I was just trying to get used to that because sometimes I'll look at it and I'm like, okay, what goes where? Because it's not really hard to like use the formula as long as you know where they go.
Mhm. Yeah, that's true. Well, I'm glad it's starting to make sense.
Yeah, I've just been trying to play catch up because like I got stuck on 3.3 for a hot minute.
Yeah. 3.3, I think, has a lot of algebra that kind of forces you to review all that stuff.
Oh yeah, definitely for sure. I mean, everything else kind of gets easier, but that one was just tough for a second.
Yeah, usually people get stuck on this section, so I'm glad you're not too stuck on 3.4.
I was trying to finish it. I mean, I'll do review as much as I can, but I was just trying to get it finished. So I wasn't like drowning in homework.
That's good. Yeah, that's true. I'm just gonna keep up because a pile of math homework is never fun.
Yeah, no, I mean, like usually I'll try having it done by like Sunday or Saturday. That way, when we start the new week, you're only doing like 2 sections and then just keep up every week.
Yeah. I agree.
Oh, I don't like to ask these questions, but I have to ask anyways. When is the next time we're gonna do another like either exam or quiz? Because I'm trying to give myself a time frame of how much time I have to review things very well so I can get familiar for the next time.
That's a good question. Let me see. We're pretty much finishing chapter 3. Let's see. Let me look at the schedule. So this week, we just need to finish 3.7. 3.6 and 3.7. So we just did 3.5. So I'll probably do 3.6 on, well, today's Wednesday, right? So next week we will finish chapter 3. So probably 3-6 on Monday, maybe 3-7. And then review on Wednesday. So the earliest I would say would be, I'll open up the exam next Wednesday and just leave it open for a week or so.
Are you gonna give us a review like you did last time?
Yeah, there'll be a review posted, and I'll try to go over it with you guys too, if possible.
Okay, that'd be helpful.
Yeah, that's a good estimate for now.
Okay, cool, awesome. Thank you, sir.
Sure.